Okay, so let's figure out how to do this. Example 14.2 says, consider the reaction between nitrogen dioxide and carbon monoxide as written below. The initial rate of the reaction is measured at several different concentrations of the reactants, and the tabulated results are shown here. So we've got this. All this information here from the data. Our goal is to determine the rate law, and then we're going to find the rate constant with the appropriate label. But let's first focus on the rate law. Now, how we're going to do this is a little bit interesting. What we're going to do is we're going to write our generic rate law. Rate equals K. Remember, it's times our reactant, so we've got NO. That should probably be NO2. All right, we've got NO2 there. NO2 raised to the M power times the concentration of CO raised to the N. Remember, M and N is what we're looking for. So what our goal here to do is we're going to set two experiments, and I'm just going to number these experiments for easier use. And we're going to put two experiments over each other to compare how the rate changes based on the concentration of those reactants. So, for instance, and we want to keep the other reactant the same. So if we look at, to find NO, if we look at this first experiment and this second experiment, we notice that CO stays the same, which means we won't have to worry about how it's affecting the reaction. So we're going to use this generic rate law right here, and we're going to set them equal to each other. So we're going to put the big one over the little one because it just makes our math easier. So we're going to put experiment 2 over experiment 1, just following this little basis right here. So we've got 0.0082, that's experiment 2, over, lost it, ooh, that's a pretty line, over 0.0021, and this is equal to K over K, which K is constant, so it's going to stay the same. Now we've got, so let's cross that out, our concentration of NO, we've got 0.20 over 0.10, and that's to the M power. And we also put CO in there, so let's check that out. We've got 0.10 over 0.10 to the N power, but 0.1 over 0.1, anything 1 raised to any power is still going to be 1, so we can also eliminate that. So we're now just looking at what happens when we change the concentration of NO2, what happens to the rate. So let's check that out. We've got 0.0082 divided by 0.0021, and we're going to just go with a fairly whole number here. So 0.008 divided by 0.002 is really close to 4. All right. Now 0.2 divided by 0.1 is obviously 2. So we have 2 to the M equals 4. So our M is going to be, you guessed it, 2. All right. So our reaction order, instead of this M up here, our rate law, we're going to put 2 right there. Now next up, we need to do that same thing for CO, but again, we're going to try to keep it where, change our highlighter color here, we're going to try to keep it where NO2 is the same. So if we look at, and CO changes, so if we look at, how about we look at 3 versus 2, right? 3 versus 2 in this case. Now we're going to use the same generic rate law. Should we change colors again? Sure, why not? So we now know rate equals K times the concentration of NO2 raised to the second power over CO raised to N. That's what we're looking for. So if we wanted to, we could go ahead and use this and use any one we want. But in this case, it's going to still cancel out for us, making it fairly easy. So let's check it out. We're going to go 3 over 2. So to start, we're going to put 0.0083 over 0.0082, which is going to be really close to 1. K over K, which is going to cancel out. We've got, for NO, we've got, NO2, excuse me, we've got 0.2 over 0.2, which we know is raised to the second power. And let's go ahead and plug that in there. All right. And then we've got 0.20 over 0.10 equals n. So if we look, 0.2 over 0.2 is 1. And so 1 squared is still 1. So we can actually still eliminate that. So we're going to do that to make our math easier. So 0.0083 divided by 0.0082 is 1. And then 0.2 divided by 0.1 is 2. So 2 to the n equals 1. So n has to be 0. So let's write out our rate law now for real. Now that we've got everything in there, we're going to say rate equals K times the concentration of NO2 squared times the concentration of CO to the 0 power, or we could just eliminate that and it would probably be better to say rate equals K times the concentration of NO2 squared. And this right here is our rate law, which is our answer for A. So let's take this into account now. Letter B says the rate constant K for the reaction and the appropriate label. Well, rate constant means that it stays constant, so it will not change. So we should be able to choose any experiment up here, plug the numbers in, and for every experiment we should get the exact same number. So pick one that you like. So we've got rate equals K times our concentration of NO2 squared. We know our rate. Let's go ahead and use the first one because it seems simple. We've got 0.0021 equals K, that's what we're looking for, times 0.1 squared. And I love how I changed from brackets to parentheses. We'll go to parentheses because that would be more correct. So now we're just going to figure this out. We know that 0.1 squared is 0.01. Yes, I had to type it in my calculator. All right. And so we're going to take 0.0021 divided by 0.01. And that's going to give us 0.21. So our K is equal to 0.21. Now the key here, and I've seen this whole question has been a perfect example of an AP Chem question. All right? They do love to ask this part about the appropriate label. So instead of numbers this time, let's go back and just put in our labels. So for rate, our label is molarity per second. So we've got molarity per second equals K times molarity squared. So we've got molarity squared on the right side, so we're going to divide molarity squared on each side. So when we bring that over to the left side, that cancels out. When we bring this over, one of our molarities cancels out, and we're left with K is going to be equal to 1 over molarity seconds, or you could think of it as molarity to -1 seconds -1. So now we just throw that on there, and we have our appropriate label. All right. Awesome. That is that question. Let's finish this out with a conceptual example. This reaction was experimentally determined to be first order with respect to O2. So rate equals K times O2 first, and second order with respect to NO. It says the diagrams here show the reaction mixtures in which type of molecule represents the relative initial concentration. What mixture has the fastest initial rate? So let's look at that. We know our rate law is first order with respect to O and second order with respect to NO. So we're looking for the one that has the most in O. Or we could plug our numbers in and see for that. That would actually probably be the smartest move. So here we have O, we have 3 O2s. So 3 to the first times 3 squared, which would be 9 times 3, which is 27. Here we have 4 to the 1 times 2 squared. 4 times 4, 16. Now looking at this next one, we have 2 to the first times 4 squared. 4 squared is 16 times 2, which gives us 32. The one that has the fastest initial rate is C. All right, thanks.